I think you should be good now.
Hello? Okay.
Like, I'm not putting as much effort as I should into actually recently. All right, guys.
Is everybody ready? All right, so I'm going to be talking about, well, I'm going to be giving an introduction to web exploitation. And this is a quick slideshow I made, but I took some slides from Adam. So who am I? I was a computer science student. I graduated in December. I am now an application security engineer at Doyensec, which is a very small firm that does security consulting. I'm OSWE certified, which is offensive security web expert. It's like one of the best certifications for web exploitation, but it still has its flaws. And then I've also done a lot of bug bounty hunting in my free time before consulting. So this is what I think that beginners should focus on learning first. First one's how the browser sends HTTP requests, common vulnerability types, such as the OWASP top 10, and just finding new vulnerabilities through reading CTF write-ups, how the browser handles cookies and sessions, which we'll cover a little bit of in this presentation. And then getting a little bit more advanced is Portswigger's Web Security Academy, which provides a lot of real-world examples and gives labs to practice exploiting. And then there's also Juice Shop, which is like an intentionally vulnerable web application that we have hosted for ufsit.club, and that you can practice on there for some of the more traditional vulnerabilities. So we have two main types of vulnerabilities, server-side and client-side. For server-side vulnerabilities, these are where the attacker directly targets the web application, typically by providing input data that is not expected by the application. And that can be sent in a wide variety of ways, such as forms, URL parameters, HTTP headers, or anything else really. And these are usually more impactful than client-side vulnerabilities, so we'll focus on these at least to begin with. And then I have a bunch of examples here. There's a very wide category of attacks called injection attacks, and those are basically where input is passed into a different context where like certain characters will have different meanings than the context that they were originally input into. So one example is the OS command injection, which is where, let's say the web application wants you to provide a host name so that it can ping it. You could provide, well, it'll pass the host name into a command with ping, but you could provide other characters to make it also run other commands because it's being passed into that command, if that makes sense. There's also SQL injections, which we'll cover more of later, server-side template injections, and a wide variety of injection attacks. There's XML external entities, which isn't so common anymore, but it'll definitely appear on some CTFs. Insecure direct object references, local file inclusions, unrestricted file uploads, server-side request forgery, insecure deserialization, and authorization bypass. So you see there's a lot of different vulnerability types here. And part of web exploitation is just learning like one at a time, and then eventually you'll see them again and you'll remember what you did for the first time you exploited it. So I'm going to explain client-side vulnerabilities now. So these usually require the victim to visit a URL, and as a result, they're less impactful. So what client-side vulnerability means is it's a vulnerability that targets the client that's visiting the web application. So in this case, the client is the browser. So, I mean, it's not directly targeting the browser, but it's exploiting the mechanisms of the browser. So the big question is, how can one website affect the confidentiality, integrity, or availability of information on another website if a user visits that website. So basically starting at an attacker-controlled web page, what can that attacker-controlled web page do to another web page that the victim is authenticated in? And so we have examples, client-side request forgery, cross-site scripting, and cross-origin resource sharing misconfigurations. I like to think of them as being in like this sort of Venn diagram almost, with cross-site scripting providing read and write access to the other web page or the other origin, technically. CORS misconfigurations providing read access, and cross-site request forgery providing write access. So that's causing a user to do things that they don't want to do on that web page. So I have a question that is, what is user input? And this depends on the context. So when you're exploiting a server-side vulnerability, the whole HTTP request, even like things that aren't even part of the HTTP request, can be considered user input. And that includes the path that the HTTP request is for, the query parameters at the end of the URL, the headers sent in the HTTP request body, and the HTTP version even. So you can tamper with all parts of the HTTP request that go to a web application, and they can all provide vulnerabilities, or they can all be used to exploit vulnerabilities potentially. But for client-side vulnerabilities, there are some restrictions, and I'm not going to go into too much depth for that for this presentation. So server-side vulnerabilities. We have an SQL injection as an example. This is when values are used in a database query, and they've been passed in either completely unsanitized or like minimally sanitized. So let's say that the server wants to use this query here. This is where it's selecting users, where the username is, and then in single quotes, the form's username that you just submitted, and then the password is the form's password that you just submitted. So what happens if form.username includes a single quote? Well, then the whole statement gets messed up because there will be 3 single quotes inside the username block. And you can use that to manipulate the SQL statement and either bypass authentication, read data that you shouldn't. Sometimes you can write data that you shouldn't. And here's an example of how that would be exploited. So this cuts off the check for the password basically by having a single quote and then commenting out the rest of the line in the SQL statement. So basically it could be used to bypass a password requirement. And in this case, this would be like the user, instead of logging in with the normal username, they're including a single quote and the 2 dashes in their username when they log in. So there are a lot more techniques with SQL injection, but I won't talk about them for this presentation. These include blind SQL injection, second order SQL injection, union-based SQL injection, and then there's also a technique to get a remote code execution using PostgreSQL. So now we have another example of vulnerability, which is an insecure direct object reference. This one's a lot more simple to understand. It's surprisingly common because it's hard for developers to implement permission checks for every single time that an object is retrieved. But yeah, so here we have an API route slash API slash users, and then an integer ID. And the way that this would be exploited is just changing the number at the end of the URL, basically, to retrieve an object that you shouldn't be able to retrieve, which can leak a lot of personal information. And there have been cases where this has been exploited with many large companies. So the mistake here is not having some sort of permission check for what object is being retrieved. And then the fact that it uses an incremental ID just makes it worse, because you can just make a loop and then go through all the IDs. Another vulnerability is a local file inclusion. So this is when the web application reads information from a file that the user provides, or a file path that the user provides. And sometimes it might not be as easy as like inputting an actual file name into a form. Sometimes the file name could be hidden in a cookie, in a query parameter of the URL. Sometimes the URL's path itself. But here's an example of how it's exploited, or at least as a proof of concept. You have this retrieve page.php, and then the f parameter looks like it's a file name for index.html, and then that shows the contents of index.html. So you could also make it retrieve other files on the system by using a path traversal. That's one way. In this example, it's using a path traversal to read the contents of the etc password file. Yes. It doesn't really contain anything sensitive now, but I think it used to contain like password hashes, some sort, but I don't think it has that anymore. I think it's just a list of users pretty much. So those are the directory traversals, sort of. So in the system, you have a list of directories going all the way down to the root directory, which is just a slash. And the way you go up a directory is by including a dot dot slash. So that's the traversal, and it goes back all the way to the root, and then goes to the etc folder or directory, and in the password file. I don't know if that helped. Yes.
So this is something that's probably like all of it. Windows, I'm trying to figure out if there's local files. Is there a file for?
So typically I don't do that because Windows is relatively uncommon for web servers now, but there are some files I would need to look that up though. I know they exist. There's some .ini files, I think, that are constant that you could use to identify path traversal. So now I want to talk about exploit chains. So usually finding a critical vulnerability requires combining two or more vulnerabilities. And so one case is using an authorization bypass to get remote code execution. And the reason this exists is because there's more functionality once you have authorization on a web server, and therefore more chances to get remote code execution. So common ways to get an authorization bypass. There are really a lot of ways, but here are like 5 ways. There's a loose comparison, which is PHP specific, or mostly PHP specific, which is where it compares 2 variables using only 2 equal signs. But in PHP, it needs to be 3 equal signs to compare the types as well. So it can lead to weird bugs where things evaluate to true even though they're not the same value. There's also the SQL injection that I already mentioned. Other logical issues, single sign-on misconfigurations, or weak cryptography and session management issues. But generally, authorization bypass is an easy way to get remote code execution because it's easier to find a path to remote code execution after you're authorized. So, and a lot of the functionality that's exposed after you're authorized is usually not as secure. So 3 ways you could get remote code execution after being authorized are with a file upload, which is by far the most common way. Debugging tools that might be exposed to like administrator accounts, or running commands, or like being able to configure configure SSH, like by uploading a key to the server. And a real life example of that is GitHub Enterprise's management console. So if somebody were to bypass authorization on that, they're able to upload an SSH key and then log into the server through SSH, because that's just part of the functionality that it has. So it's not really a bug by itself. So I want to talk more about the file upload. If you can upload any file on a server, you want to upload code that will be executed. If you can upload files to a web accessible directory, depending on the framework that's being used, you can upload PHP, Java, or .NET files, which run when the user visits those files in the browser. You could also potentially overwrite the application source code, which is very risky and not recommended because you could completely break it. And there are a bunch of other ways you have to get kind of creative with it. But even if you can't get remote code execution, bypassing authorization is a very good finding. So when you start looking at a web application, you really should focus on reconnaissance. One thing you want to know is what technologies are being used, and that's so you could save time and test for things that you might not have tested for otherwise. You also want to identify outdated and vulnerable software, because for those you could just like literally Google the exploit for it and then find a Python script in some GitHub repo that exploits it for you. But there are also some other things that are part of reconnaissance. It could be enumerating all of your targets, like subdomains. It could be brute forcing files on the server. And so things that you can do for reconnaissance include checking the HTTP response headers for version information, checking for the file extensions used at the end of URLs. So if you see index.php, you know that it's clearly executing PHP code somehow. Then you also want to look for error messages or other fingerprints associated with technologies. As I said before, you can brute force for web directories and files, but you have to make sure that's allowed first, because a lot of CTFs or companies, depending on the context that you're in, don't want you to like slow down their infrastructure or cause any denial of service. So you need to ask for permission first, pretty much, for that. And if you find a server that uses enterprise or open source software, it might be possible to find the source code from GitHub or from the Docker Hub. And then you could use the source code to look for vulnerabilities, which is much easier. So this is like completely stolen from Adam. But there's some common files that you can look for when you're testing a web application. One is robots.txt. This is in like pretty much every web server. Not pretty much. It's like maybe at least half. And it's a file in the website directory that shows which files should show up on a search engine and which shouldn't. So because the crawler used to create index results, the crawler needs to access the file, so it's usually accessible to the public. So some CTFs will place flag there. or a flag in one of the directories that are listed in the robots.txt file. Basically, everything that goes in this disallow statement in the file is things that they don't want the search engine to index. There's also sitemap.xml. This is very common, and it's once again used to help search engines. It usually doesn't have anything sensitive in it, but it's something that you should be aware of. That's very common. There's also the .git directory. So if you find this, it shouldn't be there. And CTFs like to use that as an example of a bad setup. So this is one of the directories that happens when you make a Git repository. There's also .htaccess, which is used to show it's used as a way to configure the details without altering server configuration files. So what that means is it's like a way to protect directories, sort of, and also create like rewrite rules. It's specific to Apache though. And if you can override it, then it can be used for remote code execution. So now I'm going to talk about client-side vulnerabilities. First is cross-site scripting. This is an exploit where we can execute JavaScript in like the vulnerable applications web page in the context of, well, we can execute JavaScript in the user's browser in the context of the vulnerable web application. So what that means is you can usually access cookies, the document object model, or like cause a user to change things on that page. So if you get cross-site scripting on a page, and you can affect a user with that cross-site scripting, then you can basically gain control of the user's session on that page. So you can perform any authenticated actions as that user, read any authenticated data as that user. And it's pretty severe, except the user usually has to visit an attacker-controlled web page to begin the attack. So a cookie is used. It's used by a browser to store information about a user's session, which means it's used for authentication, for example. When a user provides their login credentials, the web server will assign them a cookie, which gets stored in their browser. And then when the user visits further web pages and makes further requests to that server, the user's browser will send that cookie in an HTTP header, which can be read by the server. And that way the server knows, oh, it's this user because we assigned that user this cookie. So being able to read a user's cookies is a very important goal, I guess you could say, of somebody who's trying to do a CTF. Because if you can read somebody's session cookie, then you can just copy that and then put it into your own browser, and then you can use the website as if you were that user. Mm-hmm. Yes. Well, CTFs vary widely. Like, they're not all applicable really, but a lot of them are. And the technical knowledge that you gain from a CTF is still very applicable to real life application security.
Yeah. Okay, so I know there's like real world, like if this is on like an actual app, I can like push something or something like that. But if this was on like a CTF, if I find process scripting, would I be able to do anything with it if no user was like accessing the website?
So most likely not. It depends on the situation. So what CTFs usually do for cross-site scripting challenges is they have some sort of fake admin bot. So it's meant to simulate you providing a URL to an admin, but instead it's just you're providing a URL to the bot and the bot visits it as an authenticated user. And that's like the most common way that it's exploited in CTFs because this is really something that requires user interaction. There has to be a browser for the JavaScript to run in, or there's no real vulnerability because it'll never run and you can never gain access to somebody's session. So if it's a completely dead web application and nobody visits it, then it's useless, pretty much. So one way that you commonly test for cross-site scripting or create a proof of concept for it is you use the alert function in JavaScript. And you could do like you could do document.domain, you could do anything inside of that. But it just creates a pop-up box in the browser so that you know that that JavaScript executed. And cross-site scripting can be categorized into reflected cross-site scripting, stored cross-site scripting, and DOM cross-site scripting. In the reflected case, a payload is attached to a request that the victim sends. So if a victim visits a web page controlled by the attacker, that attacker's web page can run JavaScript on the attacker's web page, which will either redirect the victim to the vulnerable application or otherwise cause the victim to send a JavaScript payload to the vulnerable application that runs in their browser. So one way that this can be done is if there is reflected cross-site scripting using a query parameter in the URL. You could either have the victim visit that URL directly with the JavaScript payload in that query parameter, or you could have the victim visit an attacker-controlled web page, which will then redirect them to that. And by getting them to visit an attacker-controlled website, you also open up the possibility for more exploitation scenarios, such as cross-site scripting that only occurs when the body of a request is reflected instead of just the URL. So you could send a post request from the attacker's web page that causes it to be reflected in the vulnerable application. So it opens up more possibilities for cross-site scripting if you get them to start at an attacker-controlled web page. There's also stored cross-site scripting. This is when the payload is stored server-side, and this is usually when there's chat, for example, or anything where user input is stored. So it could be a username, it could be a message, it could be anything basically that the database stores. And then there's DOM cross-site scripting. This is when payload executes because this is when the vulnerable web application runs JavaScript. It has a vulnerable function in the JavaScript that handles user input in a way that causes it to execute other JavaScript code, if that makes sense. It's kind of confusing, but these aren't all necessarily separate. They could be combined. So you could have DOM cross-site scripting that's also stored. You could also have attach a payload to a request that's considered DOM cross-site scripting still. Reflected is typically when the actual response from the server contains the JavaScript. But DOM cross-site scripting is when the response of the server doesn't change, but it still handles some aspect of the request in an unsafe way. So in more detail, there's reflected cross-site scripting. This is an example where the server responds with with a query in the HTML of the in the body of the response. So this is one way you could exploit it using a script tag. So basically, instead of printing your name, it'll run the alert box. It'll pop up in your browser instead of showing your name. So there are a lot of other payloads that you could use instead of showing an alert box, but that's just used to demonstrate that the JavaScript runs. You could also use it to steal cookies. You could change sensitive information. You could do a lot of things. And the way users get exploited is by opening that link basically in their browser. So stored cross-site scripting is when unsanitized script is stored in the backend and then later executed when a user views some part of the web application. So if somebody were to, in a vulnerable chat application, somebody could send you a message with a script tag in it. And then when you viewed that message, it would run the JavaScript in your browser in the context of that vulnerable application. Yeah. So here's a DOM cross-site scripting example. This is when the response is constant. So the response of the server will always be like this, with the script tag in it and like HTML. But the actual script that runs in the browser handles the name query parameter here in an unsafe way by writing it to the DOM, which is essentially how the elements of HTML are laid out on the page. Well, the DOM is it's a way of representing a web page as an object, sort of, kind of. But the important part here is that basically the name query parameter is being written to the page. And so because it's being written to the page, you could include other HTML elements in that name query parameter and then get the alert box. It's pretty much a JavaScript object. So like you could do window.abc, where ABC is the name of an element on the page. And that's a way to get or I think it's window.document. No, I don't know. It might be that, it might be document.abc. I don't remember. But yeah, so this DOM cross-site scripting takes advantage of unsafe client-side code that runs in the user's browser. So data is passed unsanitized from a source, which in this case was I think it was window.location.search. And then it's executed in it with a sync. So one example is eval that just executes the actual JavaScript. It executes a string as JavaScript. But the sync in this case was document.write. So even though the source is in the URL, this isn't reflected cross-site scripting necessarily because it's only the client-side code that's vulnerable. The server's response isn't actually changing. So what a source is it's an entry point for our payload. This is anything that is user input. So remember when I talked about user input before, this is anything that is user input for a client-side vulnerability, basically. which has restrictions, but some examples are location, location.href, and location.search. And then syncs are different ways that there are different functions that handle that source in an unsafe way. So examples are eval document.write, then element.innerHTML, which sets the HTML of an element. And then there's a spreadsheet here. So what do you do after an alert box? If you want to send yourself data from the victim's browsing context, you could send a session cookie, depending on you can't always send the session cookie, but sometimes you can. You can also read data from the page, and then cause the victim to send a request containing that data to your server. And in this case, we have webhook.site, requestbin.io. These are like sort of public service webhooks that can be used to receive data. So if the victim's browser sends that data to that page, you'll be able to read it. And here are examples of how you could do that. One way is by redirecting the victim. You could do window.location equals, and then my webhook as a placeholder for whatever server you have that you can read data from, plus document.cookie. So this is adding the cookie to the end of the URL. And then you can just check the logs for that server and see that you received a cookie at the end of the URL when a user visited it. There's also fetch, send beacon. Yeah. So this is when script don't work. So there may come a time where the script tag is blocked or sanitized, and we need an alternative payload to execute JavaScript. One thing to note is that the script tag will actually pretty much never run in DOM cross-site scripting, because when HTML is added to the page, it usually can't be a plain script tag. Like you'll need to add an image tag, an SVG tag, or anything really. And then add a JavaScript event handler to that tag. So these are other ways to execute JavaScript. I'm not going to go into too much detail on them. Yeah. Mm-hmm. So there are some different situations. The browser does have it does prevent writing a script tag using JavaScript in most cases, I think, but I don't know about all of them. There are also cases where the developers like coded just a block list or something like that of tags not to allow in the response, or maybe they filter user input to say that it shouldn't include that tag. Pretty much. The browser needs to handle a lot of like error handlers, load handlers, like anything that can trigger JavaScript from an element. But it's also because like a server is less willing to block an image tag because they think that, like, for example, maybe they think that the only way to execute JavaScript is with a script tag. So they block just the script tag. But there is, like, the browser, if you're adding an element with DOM cross-site scripting to the page, the browser will pretty much never block like an image tag with an on-error handler. That's one thing that works consistently pretty much. It depends on the specific circumstance, but that's generally the one that I would use is the image one, even when I'm testing for reflected or stored cross-site scripting, just because it's more reliable than the script tag.
As an attacker, like what are they using to actually execute these JavaScript functions that
So the attack vector here is the victim begins visiting some sort of malicious URL, which could be an attacker's web page, or it could just be directly visiting like the vulnerable reflected cross-site scripting page. And what the attacker gains is access to the victim's session. So if they're authenticated on the vulnerable application, then the attacker gains the same level of access that the victim has. Yeah, so that's another attack scenario where if the JavaScript payload has been stored and then shown to users, then that's a much more severe vulnerability because the victim doesn't need to visit a page to begin with. But it'll run in the victim's browser when they view that stored payload wherever it's stored. But there's a lot that it could be used for. For example, if somebody had cross-site scripting on a PayPal page, then you could get that victim to visit an attacker-controlled web page, which would redirect them to a reflected cross-site scripting page on PayPal. And then the attacker would gain control of their PayPal account pretty much. There would be some restrictions, but for the most part, they would be able to like transfer money, read the victim's information, anything like that. Oh, and so one more thing I want to clarify is, so when an attacker, or when a victim visits an attacker's web page, the attacker's web page can already run scripts. So what's the big deal, right? The big deal is the attacker's web page can't read any information from another vulnerable application without that, or from another application without that application being vulnerable. So it's called cross-site scripting because one script can affect another site, basically. There's like a concept in the browser where it's like separation of sites or origins. So like one origin can't read any information from another origin. So by default, when a user visits an attacker-controlled web page, there's nothing that the attacker can really do unless another web application is vulnerable. So they can't just like fetch information from a banking application without that banking application having this cross-site scripting vulnerability. Yes. Sorry, I couldn't hear you. No. So an origin is it's kind of hard to describe, but like an example of an origin would be https://www.google.com. So that origin won't be able to read information for www or https://www.bank.com. It's pretty much just a domain. There's some more restrictions for it. It includes like I think the scheme and the port, but it's pretty much just a domain. Um, and then there's also like some semantics differences between site and origin that are kind of important, but they're not really that important for this presentation. So this is when nothing you try works. Give up. No, never give up. Uh, if it's not working due to a sanitizer, you could try to find holes in the implementation. So maybe they're blocking the script tag, but they're not considering capitalization. Then you could just make the script tag have varying capitalization, and the browser interprets it the same way. Or maybe the sanitizer URL encoded input, and maybe it doesn't sanitize that. There's actually one technique I want to talk about briefly. So there's some web applications that when they see dangerous input, they decide we're going to keep that input, but we're going to remove the dangerous part. So one thing that you can do with like the script tag, for example, is I'm going to type it out here because it's going to be kind of hard to explain. I meant to include it, but so, oh, I can't edit. Never mind. Notepad. So let's say um, let's say that the user's input is this: hello script ABC. Oh yeah, I should. O plus. Okay, so let's say that the user's input is this. One thing that web applications will do a lot is, I'm just going to put a V there. This is showing how the server transforms it. They'll just take out the script tag. So how do you think this could be broken? Does anybody want to volunteer? Yeah. Yes. So the server has to do that recursively. Let's simply just do this. She did it. I need to make this. Okay. So if it transforms it in that way, a lot of times it's still vulnerable. And this isn't just for cross-site scripting. This is for a lot of things. Another common example is path reversal. So if you provide a URL like this, and then it'll just make it it'll convert it to that. Then one thing you could do to bypass that is actually I think it's 4. And then that will be converted to your original. And this is the case where it's removing just the dot dot slash. So that's a really common mistake that gets made. And that works for like a lot of things in web applications. I'm fairly sure that this vulnerability affected Apple at one point with iCloud Mail for cross-site scripting. But I'm not completely sure, so I don't really want to be held accountable for that. What do I present from here? Okay. And there's another thing that can block cross-site scripting, and that's a content security policy, which can be bypassed in certain circumstances. But I'm not going to talk about it now. It's sort of a defense in depth measure that developers use to prevent cross-site scripting. So now cross-site request forgery. So with cross-site scripting, the attacker gains read and write access, basically. They can write information as that victim, and they can read information as that victim. Cross-site request forgery, usually you can only write information as a victim. It's kind of a generalization, but that's pretty much how it works. What happens with cross-site request forgery? The first step is a victim visits a page controlled by an attacker. We're calling it attacker.com. The attacker's page has a form, and that form submits automatically or when the victim clicks something. That form will send data to the vulnerable application using the victim's session. So the victim's browser says, oh, this is a request to the vulnerable application. I'm going to include a cookie. So the reason an attacker would do this is because they normally can't perform actions as the victim. But the way that the browser works is it sends the cookies when the victim makes a request from a different origin. Not always. I'll talk about that later. So this causes a state change of some sort, and the victim suffers in some way, probably. So let's say there's like a really bad banking application that doesn't protect against cross-site request forgery. Then they could initiate like a banking transfer from the victim's account. That's a very unlikely example, but it gets the point, I think. Or maybe they invite the attacker to their team in the application. So they have an application with teams. The team has stuff they don't want to be shared. The attacker uses this cross-site request forgery vulnerability to join the team, basically. So I'm going to talk about preventing cross-site request forgery. One way is with the same site attribute of cookies. So there are three main categories for the same site attribute of a cookie. Or first, I'm going to talk about attributes in general. When the web application sets a cookie in the victim's browser, it can set attributes for that cookie, and they're usually there are things like when should this cookie expire? Should this cookie be readable by JavaScript on the page? Or should we send this cookie cross-origin? And that's what the same site attribute affects is, should we send it cross-origin? So this is a way of preventing requests that originate from the attacker's web page from including cookies in the request, or from including cookies when the victim's browser sends a request to the vulnerable application. So same site equals none means that all requests will send cookies cross-origin. Same site equals lax means that only top-level GET requests will send cookies. And this is the sort of recent new default for Chrome and I think maybe Firefox. I don't know about Safari. So a top-level GET request is it's essentially when the victim actually visits it in their browser. So it can't be fetched in the background by an attacker's web page. The attacker's web page actually has to send them to that website, and they actually have to see that they're on that web page. So it's kind of limited. You can only perform actions that use GET requests, basically, cross origin, which is pretty rare. Same site equals strict means that cookies are never sent in requests that originated from a different site or origin. Technically it's site, but I'm going to use them interchangeably for now. So this means even when the attacker's web page redirects them to the vulnerable application, or just the application in this case, the cookies aren't going to be sent. So that user will visit that page and then they'll just be not authenticated. So the importance of this is that cross-site request forgery is only valuable if the attacker couldn't do it themselves. So the attacker needs the victim to be authenticated when the form submits. In other words, the attacker needs the cookies to be sent cross origin. Because if not, then there's no point in doing the cross-site request forgery, and the attacker could have done it themselves, basically. Another way of printing is with the cross-site request forgery token. This is when the application associates a token with a user and then requires that user sends that token in each request. So usually the application will set this token in a cookie, a separate cookie. And then for every post request, which is when a form submits, it'll compare a value in the request body to the value in the cookie. So because the attacker doesn't know the token associated with the user, the attacker doesn't know which value to send with the form. And then there's no state change that happens because it doesn't pass the cross-site request forgery check. Now I'm going to talk about CORS misconfigurations. This is essentially read access cross-origin. So CORS is cross-origin resource sharing, and it's a feature of browsers to allow one origin to read data from another origin. And the way this is done is with the access control allow origin header. So in a request from one origin to another, the request will contain an origin header saying, oh, this attack originated from attacker.com. And then the application will decide whether or not to allow access to that origin. And if it allows access, then it'll respond with access control allow origin attacker.com. And access control allow credential is true. So the way this could be misconfigured is if they don't validate the origin at all, or if they validate it in a weak way. So I pretty much talked about this already. Preventions, you just never use the access control allow origin header with an untrusted domain. So real bugs. Bugs affecting legacy and enterprise applications. Older software is usually more vulnerable. You're much more likely to find vulnerable code in a PHP application than a Python or Node.js one. SQL injections, cross-site scripting, CRLF injections, loose comparisons. They all affect older or enterprise applications more. Very little. Just because we do consulting for startups and like newer companies usually. So bugs affecting modern applications. One of the most important bugs for modern applications is server-side request forgery, which I'll talk about soon. Cross-site scripting is still super common, even though there are preventions such as templating engines that escape template variables. You can still find DOM cross-site scripting in modern applications. Client-side issues are still common, logical issues, some cloud misconfigurations, and insecure direct object references are still common. But for modern applications, you usually have to get a little more creative and explore new or unexplored vulnerability types, such as race conditions, prototype pollution, or like web cache deception or web cache poisoning. So server-side request forgery. This is when a server fetches a URL that you provide from the server like itself. It's not happening in the browser. So the reason this is important is because services can be exposed within an internal network, not accessible from the internet. And these services are usually like either not authenticated or weakly authenticated because they're protected from the internet. So it's only people that have access that internal network that can view those services. So it doesn't really matter as much if they have authentication. So the impact is, if you can get the server to fetch a URL and then give you the response of that, then you can get the server to fetch internal services and then get the response of those internal services, which could contain like sensitive information. And with the cloud, this impact goes up because there's a thing called a cloud metadata service, which can be used to fetch sensitive tokens, secrets. It stores a few different things. But I'll give an example of one that I found for a bug bounty program. I found one where the URL is provided using a query parameter. And I used that to fetch the cloud metadata service. And then they were skeptical about if that could actually be like dangerous or not. So I looked through the cloud metadata service and I found a bash script posted there. And that bash script contained another URL that was only accessible in the internal network. So I fetched that URL with using the server-side request forgery. And then that URL was a source code repository. So I could view the source code of the application. And then that they accepted as being a real vulnerability. So an example of how this could work is an image proxy that takes a URL. Sometimes this is a really common feature of web applications where they say, where they take a URL in a query parameter, they fetch that image, and then they store that image, like they cache it, or maybe they transform that image and make it smaller or add some sort of effect to it. But image proxies are a really common way to find server-side request forgeries. And this example just uses a URL query parameter to get the cloud metadata service. So when a URL is blocked, you can use IP obfuscation techniques. There are a lot of different ways to do that. The one that I like the most is using HTTP://0 instead of using localhost, because a lot of applications will block localhost, but they won't block other representations of localhost. And 0 is just kind of a funny way to represent that. That browsers and servers will understand. Then you could also use a domain name that points to the blocked IP address. Or, well, and like a subset of this is something called a DNS rebinding, which gets kind of confusing, but it's basically where the server will check to see that the domain name resolves to an allowed IP address, and then it'll send a request shortly after to that, and then give you the response of that request. So what you could do is you could have the domain name point to an allowed IP address one moment, and then when the server fetches it, then you could point it to the blocked IP address. So it's sort of a race condition where you're bypassing their check because there are actually 2 times that it makes the request, and it resolves to 2 different IP addresses. And that talk to is time of check to time of use. And then I just have parts of a URL right here. So this is really important to understand when web hacking, because I don't know, URLs occur like everywhere in the web. It's important to understand for server-side request forgery, cross-site scripting, and all of that. So first we have the scheme, which is like HTTP://, HTTP://, it could be FTP, it could be anything. Then we have a subdomain, a domain, and a top-level domain. In this case, I'm not actually sure if co.uk is a top-level domain. I don't really know, but just think of it as com, I guess, if it's not. Then there's a port number. So it goes colon port number, but that's not always included. It could just go straight to the slash, and then it assumes either 443 or 80. The browser will assume it. The path, which I'm sure most people are familiar with, there's a query string parameter or a separator, which is the question mark. And then here you have the different values in the parameters. So doc ID equals 720 and HL equals EN. So this is like the query string parameters are typically where you'd find something like cross-site scripting or reflected cross-site scripting. And then the fragment, the only time this is used is in the document object model. So the fragment is actually never sent to the server. It's only used in the browser. It can only be used for DOM cross-site scripting. You can never get reflected cross-site scripting with the fragment because it's never sent to the server in the actual request. And there are a lot of different ways you can manipulate this. I would really recommend that anybody trying to bypass like a URL restriction look into the way that URLs are formed. And here's a good link to do that. Then there's Juice Shop. I don't know if we really have time for that. Do we want to do Juice Shop? Okay. So I don't actually have a verb suite, which is what we normally use. But I'll use the dev tools. So I already briefly looked at this. It's an intentionally vulnerable application called OWASP Juice Shop. OWASP is an organization, I think it's like Open Web Application Security something. But they made this vulnerable application, right? And it just lets you view reviews and stuff like that. You can log into an account and you can search. I can say ABC. So one thing I noticed about this is ABC is being reflected here, or it's actually in the fragment, right? Because that's the hashtag symbol right there. So all this is only being used in the browser, but it's still being written to the page. So one way we could check to see if it was vulnerable is we could type our kind of small, right? There we go. Okay, so we can type like A, which is the anchor tag in HTML, and let's say like link, and see if it gets reflected. So we see that these are hidden, which means that this is being rendered as a link in the DOM. So how you would exploit this is you would use like the one of the cross-site scripting payloads that we showed before. Okay, here we go. So I'm going to use this one. I don't know if origin actually works, but okay, so that doesn't, it doesn't know what origin is, but maybe it does. Let's see. So checking the dev tools, we see invalid or unexpected token. So, okay, that's why. So looking at this HTML that's been added to the page, Yeah, I'm gonna try that. Okay, is that visible enough? Okay, so looking at the HTML that's been added to the page, we see that there are two double quotes when there should just be one. Like it's including the orange double quotes inside of the on error attribute. So we can just change that and remove the double quotes that we have in this payload. Did it do anything? Unexpected. Okay, so that's because we have the slash at the end. I'm going to remove the slash. And then it shows a pop-up box. So this is DOM cross-site scripting because it's in the fragment, which is only seen by the browser. Which also explains why we had to modify the payload some, because it's handling it in some weird way. But the way this would be exploited is you could have this link on some other web page. Like let's say it's on like let's say Google is the vulnerable page here, for example, and then you have the link right here. The user clicks this link, they get brought to this, and then the alert box pops, which gives the attacker access to their session on this. In this case, we're not authenticated, so there's not anything to be gained, but there could be something to be gained if we were logged into this page. So now we're going to look at the login functionality. So like, we can try admin, and then see how it responds. So invalid email or incorrect password. Again, the network tab. So this is something that gets stored in a database. Does anybody have an idea what to try? So we're talking about server-side vulnerabilities before. There's an SQL injection for values that get stored in a database. So let's see if it's vulnerable. And we can do that by just including a single quote. We could also include a double quote because maybe the SQL statement uses double quotes. But we're going to try a single quote for now. And then we see that this login request is made. And it responds with an error code of 500, internal server error. We look at the response, and we see, oh, it gives this SQL error. And then it even gives the query that was run. So we can look at this and see the error is right here. Like there are quotes that don't line up right. So that's pretty much what we want to see for an SQL injection. It's bad for the application, but it's good for anybody hacking it. Is that good enough? So we see this error in the response from the server. This is the SQLite error, and this is the query that it ran. So if we want to bypass this, there are a few things we could do, but like why don't we try just commenting off the rest of the SQL statement and hope that there's an admin user, because then it won't check the password. It's email, so it might not work, but yeah. So now there's not an error, which is interesting because now we know that the query has the correct format now. So the quotes match up. And one thing that you can do with SQL injections, one thing that's very common, is you can add to the end of it. So your username doesn't necessarily need to be admin. You could say select star from users where email equals admin, or 1 equals 1, which always equals true. So this statement will always, okay, I didn't even submit it, but it says I solved it. So then we log in, and now we are, I don't know who we are. admin at juice shop, because we made that statement always evaluate to true. So it just got the first user from the database, and then we've logged in as that. And that was all I really planned. Okay. So any questions? No questions? Okay, what is it?
You know, you said there could be like variable type pollution, something like that.
Prototype pollution? Mm-hmm.
You're like, or I might be mixing this up or something, but you're like, sometimes something evaluates to true because equal signs instead of equal signs.
Oh, that's loose comparison. Mm-hmm.
I'm thinking of, you ever see the things online that are like a JavaScript, a null is equal to, is not equal to zero, but a zero is equal to whatever.
I mean, that's similar. Yeah, it could be. So I'm going to open up Notepad again. One common thing is, let's say you so that's sort of close. It's not really about the memory address. It is, I mean, maybe in his case it was, but for loose comparison, this is like you have PHP code that runs on the server, and it compares like let's say if x equals 0, then then log in. Like that's probably not even valid PHP syntax, but so the fact that this uses two equal signs is like, let's say user input is a hash, or they're providing a password, and then X is the hash of that password. So if they provide hunter2 as password, then they're like they get a, what is it? Let's say they get that as, or I don't even know how many values it would be, but let's say this is hypothetically their hash, and it's in hex. So it's just printed as this, but really the representation is kind of like that. But so it's comparing this hash to 0, and if it's 0, it'll log in. Okay. So what the loose comparison is certain values in PHP don't always evaluate the way you'd expect it to be. So let's say that the user changed their password, or they changed the password that they submitted. They made it like hunter3, and because it's a hash, it'll get changed to like it'll be completely different. It'll be like that. And then maybe they try hunter4, and then it'll be, or I'm not really including numbers. There should be like numbers in these, but just imagine. Okay. It'll be like something. I need to think of a hash. Okay, let's say it's that. So in these cases, this evaluates that this right here evaluates to true for hunter4 if hunter4 has this hash. So basically, it's unexpected by developers, but in the a common sort of vulnerability is they compare a hash of some sort to something else. The hash can actually start with 0E, and then PHP says, oh, this is just 0 because it's 0 to the exponent of something. So that's why this would evaluate to true, and then you could log in. So that's like one sort of way that an authentication bypass could happen. It's a really simplified example, but that is a loose comparison. And they would friend it by just adding an equal sign there. Or it might not, it should really be that, I think, or something like that. I don't know, but they need to use strong comparisons basically, or whatever it's called, with the 3 equal signs. But that's kind of specific to PHP. PHP was really a lot of things would evaluate to true when you wouldn't expect them to evaluate to true. But they kind of changed that with newer versions, but it still exists for the most part. Any other questions? Mm-hmm. Yeah.
Do they solve that just by checking it once? Checking if that IP address is valid.
So that's one way it could be prevented by just making it happen only once. But that like that'd be really difficult to implement on the server side. So one thing that could be done is you could actually like you have to modify the library that submits the HTTP request, sort of. So like they'll probably do like a DNS check first and then send the HTTP request after. But what they should do is just have an HTTP, like just one request, and then in the library that sends the HTTP request, just prevent it from ever making requests to that to blocked IP addresses. Another way they could do it, which is much stronger in my opinion, is they could just prevent access to certain services, or only allow the input to be certain values. So like use an allow list / whitelist / whatever. So yeah, they could block requests from going just by doing it on the network level. Like say this application shouldn't be able to reach this host. That's one way. They could also just restrict do stronger validation on the input and only allow it to be certain values. But just sending one HTTP request is really, it's tricky, but it's possible. Okay, any other questions? Oh, I just touched. Personally, yes. But that's because, so that gets back to server-side request forgery. If you have an open redirect on a domain, and the server allows you to fetch that domain, then you can just redirect them. Like you can redirect them and then fetch an internal service. There are also other cases where open redirects are impactful. A lot of times they're not. An open redirect, since I haven't covered this really, this is where the server just redirects you to another page and the attacker controls whatever that page is. So it's really low impact. It's not really a vulnerability by itself, but it can be used to bypass other security protections. So there are a lot of domain names that are actually meant to do redirects. I forgot exactly what they are, but there's there are certain tracking URLs used for example, when you click on an email in Outlook, I think there's like a filter of some sort that prevents it from being like a bad link. But it'll just redirect you to that page if it's good. So that's sort of an open redirect, but it's not impactful because that's how it was designed and they wanted to do that. And they're not like that's not going to be used to escalate some other vulnerability, most likely. Hey. Well, thanks. I don't know. I just closed.